you, or I wanted to give everybody, to let everybody know that on next Wednesday, just as a reminder, we're not going to have an in-person class on Wednesday. What I'm going to do is pre-record a lecture. I'm going to count everybody present. There is a homework assignment on that lecture, but it is really short. It's our last homework that day, so it's a pretty quick one. In fact, that week, the homeworks are pretty quick because there's 2 homeworks that week, one on shear and one on local buckling, and they're pretty short. I know we're still a little behind on homework and whatnot. I'll see where the TA is on that. Homework 6.5 was due today. That was one where you sort of had 2 problems. It was the same problem, but you sort of did it twice. How'd that go? Was it pretty straightforward? Okay. All right. Today, what we're going to do is begin what I guess is our very last design topic in the class, which is discretely braced beam design. We're going to do it in 2 parts. The first part, and I don't think any other professors or, I mean, maybe there are some textbooks out there that use this, but I use the way I teach it, I look at what I call low CV value design and high CV value design. And I'm using air quotes when I say that because you'll understand what I'm getting at when I say low CV and high CV once we start getting into it, okay? So everybody get the code? What's that?
I can wait.
Go ahead.
Okay. This guy.
You'll never live it down. Okay.
Where are you working at? Coco Sings.
Okay. All right. Okay. So let's just sort of recall our model for capacity. We are going to use it today because we're going to select a beam and then analyze it. Okay. What I can tell you is that when you're designing discretely braced beams, more often than not, you are in zone 2. Okay. That tends to be the most common zone you're in when you're designing. So you design a beam and then you analyze it. This tends to be where you're at. If you're in zone 3, chances are one of 2 things is happening. Either you're designing for a really long unbraced length, like a really large LB value, or you're doing something wrong. So just keep that in mind. So yeah, okay. Now let's just make sure we're all familiar with table 310. This is the design aid that looks like a nightmare, but it's really not, because all we do is we divide out the effects of CV. And the reason that we do that is because this chart is crafted based on a CV value of 1. Okay, and it's this step right here that really differentiates what I'm calling low CV value design and high CV value design. So we're going to start off with looking at small or low CV values. We then go to the chart and we, on the x-axis, look at our unbraced length, and on the y-axis, we're looking for our moment of interest. And in this case, in design, our moment of interest is whatever our maximum moment is divided by CV. Okay? And so we look up to the right and we find that point. So last time we looked at this example, we found that point, we shaded this region, and we said anything that's in this region is a safe design because it means that we are selecting something that has either a larger moment capacity or a higher unbraced length. So anything there is safe. And we look up to the right and we find the first solid line that's plotted because within that region, the solid lines are the most economical. Like right here, 175, 167, 146. That's the light one, so that's the one we go with. And we try that section, okay? And when we say try that section, we mean we have to analyze it, okay? So let's go into the process of design, okay? Now to be clear, the process of designing a discretely braced beam is, at a 30,000 foot view, the same process for a continuously braced beam design. The only difference is you're using different design aids and different models to compute capacity, but the idea is the same. I mean, the first thing that you do is you compute a maximum moment, a maximum shear. You do all the structural analysis. Remember, we have a self-weight that we need to assume. We typically assume anywhere between 50 and 100 pounds per foot. The only thing that changes in step 1 is that we also need to get a CB value. We need to compute CB. We're going to try whenever possible to just look up CB in table 3.1. When possible, we'd like to avoid computing it. The next thing that we do is, just like last time, we compute a moment of inertia based on whatever deflection limits are present for the problem. So after step 2, and when we were doing continuously braced design, we said after step 2, we're going to have our analysis results and our required moment of inertia. Same thing here, although we're also going to have a CB term. That's going to be an additional term that we need because we're dealing with discretely braced beams, not continuously braced beams. Then what we're going to do is we're going to look up a trial section. Now, last time we were looking at that trial section in table 3.2. Now we're looking it up in table 3.10 because it's discretely braced. We go into table 3.10 with this on the x-axis, this on the y, find a shape that works. And then what we do is we go to the moment of inertia chart, or the moment of inertia, and we ensure that it has an adequate moment of inertia. If not, we abandon all this and we go to table 3.3. Again, the same process as before. Nothing changes. The only thing that changes is different design aids, because it's a different animal when it comes to bracing. And then the last thing that we do is we analyze the trial section to verify that it works. Now, I got a little note here on step 5, and this is really what's going to differentiate low CB value design versus high CB value design, okay? Whenever we look at discretely braced beams, this assessment of moment capacity is highly necessary, okay? And this has nothing even to do with the assumption of beam self-weight. See, in continuously braced beam design, what we said was, all right, if we assume that the beam weighs 100 pounds per foot and we pick a W24 by 76, analyzing it really isn't that big of a deal, because if we assumed 100 pounds per foot and it weighs less than that, then we know the beam's fine. But here it's another animal. Okay, here we desperately have to analyze the beam. And the reason why is because that these high CB values can generate false positives. And more on what false positives mean later. I don't want to get too far down the rabbit hole on that. What I want to do is let's get familiar with the process today, and then next lecture we'll say, okay, what happens if we have these false positive situations? And again, we look up our shear capacity and we check our deflection capacity. And that's basically the process. The only thing I'll mention moving forward is that sometimes when you're using table 3.10, sometimes the lines are kind of like really bunched up. So if you found a given point, sometimes it's easier to do this. Sometimes it's easier to just track upward. So if you're having a hard time reading it this way, maybe try and look upwards. Either one will work. Okay, so I'm just giving you that as an idea that if you're looking at the table and you're like, I can't read this, do that. Okay. So with that, let's go ahead and just get right into an example. Okay. So we're going to design a discretely braced beam for this load. So we have 1,000 pounds per foot of dead load, and we have 3,000 pounds per foot of live load. Okay. The dead load does not include the beam self-weight. So the self-weight that we see, the dead weight that we see here is superimposed. It's on top of the dead load. We're going to assume that the beam weighs 100 pounds per foot. Okay. I'm assuming a little bit of a heavier load because discretely braced beams tend to be heavier than their continuously braced counterparts. So to put it in perspective, I have a 24-foot beam with these loads on it. If I were to change the problem and say design it if it's continuously braced, design it if it's discretely braced, the discretely braced beam will tend to be heavier. Okay, so because of that discrete bracing, the beam is weaker. Okay, so you'll need a heavier beam to be able to withstand those loads. So we're going to assume 100 pounds per foot for the self-weight, and we're going to ensure that we meet a live load deflection limit of L over 360. This is a very realistic deflection limit for most commercial building design. So this is a really realistic problem. This is about as realistic as it gets. So let's get right into it. All right, where'd my pen? There's my pen. Whew. Okay, so the first thing that I'm going to do before I do anything regards to table 310 or looking at beams is I'm going to perform the structural analysis. Okay, I have a simply supported beam with a uniformly distributed load. I've got dead loads and live loads on it. So I'm going to go ahead and handle that part. Okay, so actually, let me do this. Let's do step 1. Let's do it like that. So we've got and we're going to go with a 0.1 kip per foot. Like that. And then like that. Okay, so we have a simply supported beam subjected to a uniformly distributed load, so we've got some structural analysis to do. So okay, so the first thing that we're going to do is compute our dead load response, which is this right here. I'm going to go ahead and do that part for you right here. I'm getting 13.2 kips and 79.2 foot kips. I've got to believe by now that you're familiar with that. Notice that I'm saying dead weight plus the self weight of the beam because I've got to add that part as well. I have the live load. I have this, and this is going to be 36 kips, and this is 216. Okay, so again, it's just WL squared over 8. I'm using the same formula for both because it's the same loading for both. Okay, and remember, I do want you to by default kind of think about computing these separately, simply because if you have a live load that's not distributed, if it's a point load or a series of point loads, then you kind of need to handle it that way. So just make sure you're thinking that way. Okay, so excuse me, our factored load. We have the shear, which ends up being 73.44, and the moment, which is 440.64. And I hope you're okay with me going ahead and just doing that, simply because, I mean, we've been doing this a lot here recently, so I hope this isn't like complicated at this point. So, everybody okay with that? Now, something else I want to go ahead and figure out on this step, which is new, we didn't have to do this before, is the moment gradient modifier. I'm going to need your help on this one. So I want to know what is the moment gradient modifier for this problem, okay? And for this problem, I have a simply supported beam subjected to a uniformly distributed load bracing I have is here and here. So there's only one unbraced segment. So what is CB going to be for this problem? 1.14. So this is one we can look up. And the cool thing about this is that CB doesn't change as a function of the load. Like if the load goes from 1 kip per foot to 7 kips per foot, it's still the same CB value. Okay, so after this step, I want to make myself a little reference here on the board. So what I'm going to write is the shear, the moment, which is 440.64. And CB, just so we have it like readily available, I'm just going to have that over there on the side. Okay. Is everybody okay with this so far? Okay. Now the next thing that I need is my deflection limit. Okay. Now I sort of put this in a separate step because sometimes we might be doing a problem that doesn't have one. So we have that. Okay. So first off, let's see, what do we got here? The first thing that we need to determine is our limit, which the problem said that we had to limit deflections to L over 360. So this is 24 feet over 360. Am I missing anything?
Times it by 12.
Exactly. Okay, so 24 times 12 over 360. I can go ahead and give you that one. That one's 0.8 inches. So the next thing that we do is we compare that against what's the maximum actual deflection on the beam. Okay. So that's the actual deflection on the beam, okay? And so I'm going to set these two equal to one another, and I'm going to solve for Ix. Now, one of the things I'm going to go ahead and put here is the following. I'm also going to put I'm going to do this, so maybe here's what I'll do. Maybe I'll do it like that. Because when we compute deflection is going to be computed as 5WL to the fourth over 384 EI, but I know I'm going to need to multiply it by 1728. So I'm going to set this over here. I'm going to set this expression equal to 0.8 inches. And then I'm just going to solve for Ix. And how do I solve for Ix? Just swap the 0.8 and the I. So a sec on this. We'll call this the live load deflection limit. So we've got a big old fraction. 24 feet to the fourth power, don't forget that. So we have this calculation here, so tell me what we get for IX required. We'll stick this value up here as well. This one I am going to get your help on.
965.30.
965.3. Okay. Second?
Yeah.
All right. Okay. All right.
Wouldn't that be interesting? Is that a 4 or is
It's
it
supposed to be a 4. It's a very poorly written 4.
yeah.
Yeah, let me read it then.
It's not necessarily your pen. It's more like the people who make glasses do a shitty job. Poor job. He's not gonna have ads on this video.
I don't have ads on me. Okay. All right. Okay. All right. Oh man. Senioritis. Okay. So we're now in design mode. Okay. Design mode means what we need to do is select the shape. Now we're going to select the trial shape. And we're going to select that from table 310. So this is what we did last time with the beam chart A. So what we're going to do is we're going to go into this chart with certain values. We need a value on the x-axis, we need a value on the y-axis. Okay? The value on the x-axis is LB. What is LB for this problem? We haven't talked about that. What is LB for this problem?
24 feet.
Say it again. It's 24. It's the distance between braces. It just happens to be the span length for this problem because the only braces are at the ends. So for this problem, LB is 24 feet. Now on the y-axis, we look up a moment, but we do not look up MU. We look up MU over CB. Okay, we look up MU over CB because the chart is designed for a CB value of 1. Okay, so we're going to go, what was MU again? This is why I put it up here. 440.64. So what do we got?
386.5.
386.5. So that's what we're going to do. We're going to look into table 310 with an x-axis value of 24 feet, a y-axis value of that. We're going to find that point, and then we're going to find the first solid line trial shape that we can. So from these, we're going to try a certain value. And this is important. I want to make sure we're all comfortable with this. I want to make sure we all find the same value. So when somebody finds one, I want you to tell me.
You were in the wrong one.
310. What's that?
W18
Okay, W18 by 76. Everybody brought their manual today. Everybody brought their manual. How? You brought your manual, didn't you? That, see, I saw that look and was like, Dr. Mike, I hope he doesn't like look at me over here. I know things about stuff. Let's check to make sure everybody's able to find it. You able to find 76? 76? Yep. 76? Okay, okay, keep looking. You got it? What about you? You still looking? Still looking. Still looking. You got it? Still looking? Take your time. You found it? You got it? Yeah. You look like you're on the right spot. Right spot. What about you?
Yeah.
You got it? You got it? About y'all, about you here. You got it? You got it? You got it? You got it over here? Okay. So, oops. I'm sorry. So, 386 is about right there. 24, so you're about right here. You're going to look up and to the right for a solid line. How's everybody back here doing? Y'all able to find it? Okay. So it looks like everybody was able to find the W18 by 76. Okay. So, a couple things. The first thing I want to do is I want to go to table 3.2. I want to find the W18 by 76. Now I want to go to the ZX tables and I want to find that W18 by 76. Okay. What is the moment of inertia of a W18 by 76? I mean, notice we could find that in table 1.1, but we can also find it in table 3.2. And I'm wanting to find it in table 3.2 because we're going to need a lot of other stuff in table 3.2.
1330.
Say it again?
1330.
1330. So will this beam, if we choose it, will it meet the deflection limit? Yes, it will, right? So it is a worthy beam to analyze, okay? So we'll say okay. So now, it's time to do some analysis. So let's analyze the W18 by 76. Now, how heavy is a W18 by 76?
76 pounds per foot.
76 pounds per foot. What did we assume was the self-weight?
100.
100. So this is heavier than our assumption or lighter than our assumption?
Lighter.
So if our beam has enough capacity to withstand these, we really don't need to update these, right? These are fine. So what I'm going to do is say the following, okay? is lighter than our initial assumption, therefore just reuse them, okay? Just reuse them. Now, for the W18 by 76, okay, we need to determine the moment capacity, okay? So I want you to tell me, we've got a flow chart that'll help us determine the capacity. How do I determine phi mn for this section? What do I do?
You have to find LP, LB, and LR.
There we go, exactly right. So let's look up LP and LR. What is LP and LR for a W18 by 76?
9.22 and
9.22 and what?
27.1.
27.1. So from these, which zone are we in? 2, because LB is 24 feet, right? We're in zone 2, okay? Now zone 2, let me go back to my flow chart here. Here's our expression for zone 2 capacity, okay? So what terms are we going to need? We're going to need CB, we're going to need phi MP, we're going to need phi BF, we're going to need LB and LP, okay? So let's just start writing this stuff down, okay? So CB is 1.14. What's phi MP?
611.
611. Okay. One interesting observation that we are going to make next time is we are going to look at phi MP. We're going to look at this term right here. And so we don't need to do anything with that today, but I just want you to keep those two numbers in the back of your head, because we're going to make some behavioral observations next time. All right. What is BF? Phi BF, I should say.
12.8.
12.8 kips, okay? So we have LB, 24 feet, and LP of 9.22 feet. So what we're going to do is, here is our moment capacity expression. So what I'm going to do is I'm going to compute the top row, and then I'm going to say phi mn is the minimum of that top row in phi mp. So let's go ahead and do that. All right, so what do we get for this? This is just linear interpolation.
480.87.
480.87. Second. So essentially, phi mn is the minimum of all that, and that's just sort of my way of writing that big line. I'm kind of lazy. And so we get what we calculated. Now, here's something I'll tell you right now. So we are dealing with what I'm calling low CV value problems. Low CV value problems are when this happens, when this is smaller than that. High CV values are when it's the other way. High CV values are if we had a CV value of like 1.7. If we had a CV value of 1.7, it'd probably be the other way around, and this one would be our minimum. That changes things. It also changes things from an iteration perspective. So we'll talk about that next time. So here we've got .87 foot kips as PMN. What do I compare that against? I compare that against this right here, right? And what does that mean if MU is 440.64? Exactly. My performance ratio is 91.6%. Right there. So the only thing left to do is compare shears, which what is VBN for a W18 by 76?
236.
Say it again.
236.
236 or 232?
232.
We compare that against VU of 73.44. So are we okay? Yeah, of course we are. And then finally, here's what I'm going to do. If you want, you can compute deflections. What I'm going to do is just say IX required is 965.3 and IX actual is 1330. So that's okay. And that gives me a performance ratio of just 72.6. And all I do is just divide the two. That is a way of checking deflections, is just to compare those. So can we use this beam? Oh, I forgot to print see that. Can we use this beam?
Yeah.
Yeah, we can. So that's our answer. Boom. That is our answer. What do you think? That's not hard, is it? All right, I want to introduce this idea of high CV values today, but just to make sure we're all on the same page, so I'm giving you a homework today, and I think this is 6.6. Yeah. So here's the problem that I'm giving you, okay? And the thing about it is, so a couple things. I'm giving you the beam. The only dead load on the beam is the self-weight. The live load are these two 20 kip point loads right here, okay? Now, I want to talk about this beam real quick because I don't want you to overcomplicate it. There are three segments, unbraced segments of this beam. This, this, and this. But let's just have a conceptual discussion. As LV goes up, what happens to capacity?
Goes down.
It goes down, right? Because the longer the distance between the braces, the weaker the beam. So if all we were considering was LV, which segment is the weakest? Segment 1, 2, or 3? 2. Okay. We can also use table 3.1 for CB, okay? Because the dead weight is so small compared to the live loads, we can just use table 3.1 to compute CB. And when you have a beam like this with 2 point loads right here, what's the CB between here? What's that? No, we're only considering the point loads. 1.01? Should be just one. So the CV value out here, what's the CV value out here? So let's think about this. We have this segment with a really small LB and a really high CV value. Or we have this segment with a really long LB and a really low CV value. So if you're designing, do you even worry about this? No. So just consider this segment, okay? So that was my big point I was wanting to make. Your deflection limit can't exceed L over 240, which is common for roof segments and whatnot, and there we go. Sound good?
Are we looking at the third points one with the distributed load? Is that where you're getting the values from?
Yes, and I know some of you are thinking, well, those aren't third points. It doesn't matter, and here's why. Because if we look at the beam like this, let's just put a point load here. It doesn't matter what it is, okay? So P and P. It doesn't matter what it is, and it doesn't matter what this distance is, right? We'll call it A, right? This dimension here, or this reaction here, is also P, right? So the shear diagram goes up, over, down, no shear, down, over, like that, right? This is positive PA, this is negative PA. So the moment diagram looks like that, right? Okay, what I'm saying, here's what I'm saying, okay? This maximum moment is PA, right? I don't care if the braces are here, 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 it doesn't matter, right? Because it's symmetric, between braces, we have constant moment. And if between the braces, the moment is constant, CB is 1. Here and here, the moment is linear, okay? And it's pretty easy to show that if this is 0, and this is a value, and this is a line, and you have a brace here and a brace here, CB is 1.67. Okay, you can derive that. I'm just saying you don't need to consider those end segments at all. That's what I'm saying. Does that make sense? Okay. All right. I want to just make a point about something real quick, and this is not going to affect your homework, but I really want you to think about this. I want to give you an idea of what this high CB value thing is. Okay. All right. Everybody open table 310, because I want to show you what I mean by this false positive issue. Okay? Just help me out with something. I want you to pick a section with the following data. So, watch up here. So we're going to pick a section for a following data. So imagine we just did a design problem. I got, here's my moment, here's my CB, here's my LB, etc. So how do I use table 310? I go to the table 310, and I say, let's divide out the effects of CB, and let's go for an LB of 20 feet and an MU over CB of 510, okay? So I want you to help me out. What section are you going to find for this configuration? Just help me out. A W27 by 84? It's either 27 or 24. I can't remember. But you're on the right track. Okay, W27 by 84? Let's see if that's what I got. I can't remember. Oh, I got a 24 by 84.
You got
I think it's going to be fine either way. I think my point's going to be made no matter if we use the 24 or the 27.
24 by 84 is dotted, which is, I guess, why we were.
Oh, is it dotted?
Yeah.
Oh, okay, but, okay, well, all right. Let's say it's a 27 by 84. Okay, 27 by 84. What's VMP for a 27 by 84? I'm just curious. Let me just-
915.
915. Okay. Okay. My point's still getting made. Okay. Does anybody see a problem? What? Think about it. What problem is this number going to generate? Tell you what,
It's less than the MU.
it's less than mu. Is this beam going to work? No, it's not. Remember, what does our chart look like? Our beam chart looks like that, right? And then CB tends to make that chart really big, right? But we cut the chart off at MP, right? What I'm saying is that sometimes when you open up table 310, if you have a really, really high CB value, you can generate a false positive. I had 24 by 84. I'm going to check that because I could have sworn I had a 24 by 84. This is bugging me, but I'll look at that here in a little bit. But whether it's a 24 by 84 or a 27 by 84, it doesn't really matter, because if you use the 27 by 84, it's not going to work, because CB served to falsely magnify the capacity, as it were. Does that make sense? So the point is, this is a false positive. So how do we handle that when we have a really high CB value? That's what we're going to talk about on Friday. Okay, so now you got me. I want to look at this real quick before we leave. 510. I guess you're right.
That's a pretty big one on the state counter.
Oh well.
It's on the PowerPoint slides and everything.
It's on the PowerPoint slides and everything. I'm gonna check the last menu. Maybe they added some shapes or something. I don't know. But, oh well. All right, we'll fix that next time. I'm gonna pull up the code one more time. I will see you all on Friday.